Let's talk about scanners now. I've got 3 different sketches here of 3 different ways of moving the cantilever relative to the sample. And they all have that function, but there's some advantages and disadvantages to each of these configurations. The one on the left is the one I've been sketching. It's the configuration of the AFMs that I use for teaching. Everything's in a nice package above the sample: the scanner, the cantilever, the laser, the photodiode, such that underneath the tip there's a lot of space for samples. So you can use big samples and thick samples, and it's very convenient that way. The disadvantage is that the laser, in order for it to track the cantilever, has to be inside the scanner, and that configuration can be delicate and tricky. In comparison, the sketch in the middle, where the cantilever, laser, and photodiode are fixed and above the sample, and the sample is on the scanner, that is a simpler configuration. However, it's limited to small samples. Both of these first two, you see that the scanner does X, Y, and Z all in one. So that's good in terms of having a very compact component. This is usually done with piezoelectric ceramics. But it has a disadvantage that typically it doesn't move perfectly orthogonally. So in fact, it sort of moves in a bow like this or like this, with the additional complication that if the sample is thick or thin, you get a different calibration factor for the amount of applied voltage, because this is now tracing out a bigger arc, a bigger radius, than if you had a thin cantilever like that, a thin sample like that. So a way around decoupling and making motion more orthogonal is to put the sample on a stage that moves in X and Y, and put the cantilever, laser, and photodiode on something that moves in Z. This has the advantage of it being very compact, and you can move it faster in Z. In X and Y, the rule of thumb is the bigger it is, the slower it goes. Here's an example of why you should check your scanner periodically. Both images here are of the same 10 micron grid. You see they are 100 by 100 microns, and we see 10 periods of the grid. So the voltages that we apply are appropriate, and the conversion factors are pretty close for converting volts to displacement. However, take a look at the shape of the squares. On the left-hand image, everywhere we look, a square is a square. On the right-hand image, in the lower left, we've got a horizontally oriented rectangle, and in the upper right, we've got a vertically oriented triangle, or rectangle. The unfortunate thing is that scanners don't necessarily work linearly. They don't respond exactly linearly with the voltage applied to them. So frequently, you need some linearization. And on the left, we've got a closed feedback loop acting as compensation. It compares the scanner's actual position to where it should be and makes an adjustment. On the right-hand side, we turned that off for purposes of this demonstration. I recommend that you get such a sample, the sample where you know shape and size, and that shape and size should be on the same size scale as the features of interest in your upcoming experiments. So for example, If you're lucky enough to have great resolution and you can discern individual atoms on your surface, which is unusual for an AFM working in air or liquids, but still possible, you can just use the atoms in the surface of a material that value the interatomic distances in crystals. Those are known very, very well. Unfortunately, for micron scale features, the better the feature size is known, the more expensive the samples are. Another way to check if your scanning is working well or not is to zoom in on a feature from a large size scale to a small size scale. So here we've gone from 100 by 100 microns to 10 by 10, and we wanted to zoom in on an intersection of the low spots and have that be in the center of the picture. On the left, you see we've been almost successful with that. We were hoping more that these dark areas would be truly in the middle, but that's not too bad. Whereas on the right, again, that feedback compensation system was turned off, and we're nowhere near that orientation. And in fact, if you look at the dust particles, they're not the same here and here, and as well as the markings. So we're not even anywhere close to this intersection that we had intended to zoom into. For Z calibration, it's the same idea. You need to have a sample with known sizes, this time size of step. Use a sample with step sizes in the micron scale if you're going to be measuring samples with micron height differences. Use a sample, perhaps the atomic steps of the sample, if you're going to be measuring changes on the angstrom level. I do have a caveat. If you're tempted to use a sample that is a compliant material on top of a stiff material, and you think you know the height of that, well, you have to be very careful, because it could be that your tip indents the compliant material much more than it was indenting the stiff material, and then you won't get a good measure of the height. There's an alternative way of calibrating your Z for your scanner, and that's to use a coherent light source, such as a laser. Coherent means that it puts out light waves that are in phase. You break up the light beam into two paths, and you recombine them at the photodiode. If at the photodiode the light waves are in phase, you get a strong signal, as sketched on the left. If when they recombine at the photodiode they're out of phase, sketched on the right, you get no signal. How that works in AFM is following. You have your cantilever, you have an angle of repose for that cantilever. It is near a sample. You bring down your light beam, and this time you put it half on and half off the sample. Here's the half coming back from the cantilever. Here's the half coming back from the sample. Now, if the sample is perfectly flat, of course this doesn't happen. You don't get parallel beams coming off. You would just have the light being reflected straight up. But most samples aren't perfectly smooth. Note that after this plane here, those beams are parallel, and so there's a path difference only in this space right there. This angle right here corresponds to 2 theta. And so as you bring your cantilever up and down a distance delta z, then that path length that I have sketched in white the change in that path length is equal to the change in z times the quantity 1 plus cosine 2 theta. So what we should expect if we plot the photodiode voltage as a function of delta z is a modulation of that photodiode voltage as those two paths, two beams of light interfere. And one period here should be equal to the wavelength over 1 plus cos 2 theta. In other words, back at the equation at the bottom, every time you go one wavelength, path length difference, you get a modulation. Thus, if you don't have a sample with calibrated step heights, and you don't want to spend the money, and you have a coherent light source that you can calibrate with a spectrum analyzer or another means of checking its wavelength, then you can use interferometry for your Z calibration. In summary, we've been speaking about scanner configurations, problems with scanners, how you need to have a calibration sample or two, and by the way, if your scanner needs adjustment, you should consult with your manufacturer how to do that. And finally, interferometry as an alternative for Z calibration. I've enjoyed making these lessons. This is the last lesson on fundamentals and instrumentation for AFM, and I'll continue with making lessons on interpretation of force curves, and I hope you'll join me for those.